library I found is missing NO for just generally visualizing missingness. Guess I may not have mentioned this at the beginning. For a lot of the tools for dealing with missing data, they're not that well evolved in Python, so there's no, I don't particularly advocate any library over any other right now. But I think as far as displaying missing data, this one is probably the most mature. Okay, so this is taken from I actually got this from Kaggle, the data set from Kaggle. It's has to do with housing in London. And it's known to have some fields missing. So again, as part of any exploratory data analysis, one of the first things you should always check for is what's missing in this data set. And we're going to go ahead and assume here that if it's blank, it comes in as an NA, it's missing. And you can see here, this gives you sort of your general statistics. The bar graph method of missing NO will basically give you these statistics, but in a nice bar graph format. And so a lot of these other options, and you can look this up in the missing NO documentation, can help you put in a prettier display. If I actually just did I've already kind of pre-programmed these with quote unquote nice values, because I think, to be honest, if I were to do just the defaults, it comes out a little bit ugly and unattractive. So. But the thing about this is it'll give you at a glance. Actually, I believe this is the opposite of missing. This tells you is a bar graph of, this is a bar graph of actually what's there. So all the ones that are all the way filled up to the top means nothing's missing or very little's missing, and the ones that are further down mean more are missing. And in this case, they sort it by the degree of missingness. So the stuff on the far right has the most missing, and those on the left have either none or the fewest. Also, the tutorial I mentioned up here, actually, I might as well just bring it up so that you can see. You'll see that it's very much the same type of thing. I did not include, he uses two data sets. One was a Starbucks store location data set as well. I wasn't quite sure what the distribution rights were for that data set, so I didn't want to include it. So if you're not getting enough out of this tutorial, I would encourage you to go to the other one. The link is in the notebook. Okay, another way to look at missing data is using this matrix format. This basically, it's kind of this will help you at least visually look at co-missing data. And this kind of goes back to, a gentleman in the back asked about, identifying patterns. This is potentially a tool to help you identify. You can kind of see that number of houses and area size probably are co-missing. You kind of, any straight line across that's white is a value that's missing. It has this feature here on the side called spark line. I'm not sure if I find that particularly useful, but it's sort of a histogram of what's missing in the other direction. It is a visual aid, but I think the heat map, personally, I think is a little more useful for that, identifying patterns. So this is basically, it's almost like a correlation heat map. So area size and number of houses tend to be missing at the same time. Well, they're missing at the same time all the time when they do. So number of jobs and population size, those two values are missing concurrently the most. Okay. And probably the biggest thing that might help you, like, especially if you're trying to identify a monotonic relationship, is this last feature. I personally don't really know that much about dendrograms, but what this shows is when you have clusters of missing data, which are more associated. And later on with the imputation techniques, you'll probably want to start with the way a lot of them work is that you start with the columns with the least data missing. And so these features are useful for predicting this one, stuff that's predicting missing values in this column, and goes on so forth. So life satisfaction is probably the one that's you're going to want to use everything to predict. At least that's my take on how this could be useful. So this is sort of a very short module, partly because in my experience I don't use it that much, but it is not a bad way to kind of get a good glance at a data set. I mean, if, for instance, this matrix looks like Swiss cheese, you might be in bad shape. So that's, whereas if a lot of it's in straight lines, it might indicate there's a predictable mechanism. And so with that, it's easier to address. So that's, it's kind of a short module, and that really is all I have to say about it. Aside from, just seeing how bad the damage is, it can help you in predicting or guiding your imputation tools, which is what the next section will be, we'll introduce. So any questions on this or anything that we've talked about so far? Yeah. Yeah. Yeah, I believe the matrix plot does it in row order. I'm not 100% sure, but I think that's what it does. Otherwise, you'd stack it and you'd see, big swaths of white. So my guess is here it's the numbering on the left is probably the row number. Okay, so before we keep moving on, did you guys have any questions on sort of the theoretical stuff we talked about before the break, now that you've had some time to let it sink in? Or okay. All right, so to be honest, personally, I think it gets a little more fun going forward. Less. All right, so here's how we start. Okay, so I want you guys to load the first few cells just to make sure that the data is loading for you. So if you're not able to load the first two cells, let me know. We'll get somebody to help you. If you're all running out of binders, it should probably not be a problem. It should all be there. Okay. So I know a few of you have mentioned that the way you quite frequently deal with data sets is you simply you just simply drop the data. Well, this is referred to in sort of the missingness world as deletion, and it works great for MCAR missingness. And there's two types of deletion: list and pair. List is what you would think of, and that is if that observation has a missing data, just chuck it. You don't need it. And it's really simple to do. In pandas, you just simply do a drop NA, and all the columns with missing data are gone. And so, just as a comparison, this I believe is our Oh, this is our MAR example. This kind of demonstrates why for MAR it's bad, because you've actually, in this case, by doing so, you have a 10 and 12% difference in mean. So if this were MCAR, I think we did load the MCAR data set. You can see here, in this case, it is more justified. Just simply dropping it, the values, the percentage difference between the mean, median, and standard deviation is relatively small. It's under 1%, under 0.5%. And that's not bad considering that 20% of the data is missing, and we haven't changed the statistics really significantly. The other reason is, the other cause is what they call, the way to treat it is what they call pair deletion. And that's referred to because a lot of operations do things in pairs, like covariance and correlation. So pair deletion simply is, let me go explain this. This is, I believe, this is the formula, without all the special notation, it's the formula for computing the covariance. The difference here is that if x sub I or x sub j, k is missing, we just delete that particular term. So we only sum over the k's where those values persist. So if they're missing, we drop the whole pair. So we're not dropping the entire row. So let's say that you have 4 columns, A, B, C, and D. And if you're computing the correlation between C and D, there's no reason to drop that row. But if you, let me back up, and A is missing. But if you're computing the correlation between A and B, A is missing, so you drop that one for that particular row. But you don't need to do it for C and D because they're not missing. So that's what pair deletion is. There wasn't really a simple example to do right in the code. But when you do, you may have noticed that when I did, say, mcar df, and I do the correlation, right, it doesn't complain that I have missing values. All right, so probably one of the questions that should have been asked is, well, why didn't it say, well, you had missing values? Built into the correlation functions, and the covariance function is pairwise deletion. So if the column is actually missing, the 2 columns that you're actually computing the correlation for have no missing values, it retains it, but if it is missing a value, it just drops that particular row in doing the calculation. So in a lot of ways, when you use these pandas functions, pairwise deletion is already built in. So you don't really have to worry about it, but it is something to be mindful about when you're actually executing this. And I think the other one, let's say mar df.cov. I mean, also mean and median as well, but I wouldn't call it pairwise deletion because you only have one value, so it's just simply a deletion. But anyway, so those are 2 demonstrations. Okay, this next topic is a little tangential to where the rest of this is going, but I think it's worth mentioning just for completeness sake. If your data is time series or there's a spatial, and the other thing is, or spatial connection or geometric connection, you can interpolate as opposed to impute. And that basically means if your data is continuous in some way, you can fill in any missing values by extrapolating from what the existing ones are, the neighboring ones, for instance. So this is a simple example that's in the data set. Again, let me know if you can't have trouble seeing it. This one actually has quite a lot of it missing. Let's see, so, okay. I think actually in my notes. Originally I had the, let me just do the defaults. It's ugly, but, oh, I did not include that. You'll need to import that if you want to follow along. So this gives you, oh, I just misspelled it. Yeah. Yeah, so you can see that the white is what's missing. So you can see that actually a lot of it's missing. And in fact, if we do the typical thing, data frame is null. So each of those has Y and Z have 40 missing, and I think that's out of 100, maybe. Can't remember if it's out of 100 or 60. Well, anyway. Okay, and just this next one is just to, I'm coloring, creating a missingness. Oh, this is just because I want to color some things in here later. So that's just to set up a color map and also identify which Y values are missing so that we can color them differently. That's all that is. Okay, so the most basic interpolation technique is backfill or forward fill, which is just taking the your last observation and just duplicating it forward, or taking the next one and copying it backwards. I've seen this listed as an imputation technique, which I really find there's no justification for if you don't have any correspondence between the rows. If there's no connection between the rows, how can you take the one before it to fill in? So, so that's why I listed here as an interpolation technique. So if we do that, you can see that the red dots are the original one, and I think this is a forward fill. The blue dots are the corresponding forward fill. So you can see that you have the red dot, and then they all still quite correspond to what I expected, but I think actually some of the red dots are covered. Okay. Anyway, I'm not a huge fan of doing the fills, these forward and back fills anyway, even for interpolation. If you know it's interpolatable, you got better techniques anyway. This is just set up as a generic interpolator cell. And really what it does is it interpolates Y and Z, and then we'll plot the Y and Z on it'll do a scatter plot of the Y and Z and color the missingness. So this is the basic one. This is linear interpolation. So the data looks like this. It turns out that there's two others that are supported by, oh, I should back up. I'm using SciPy's interpolate module to do the interpolation. I'm sure many of the packages have this. That was just the first one I found when I did a Google search. You can run this for a quadratic. As you can tell, actually, my original data set, I just took sine and cosine and clobbered a bunch of stuff. So that really is just the data should come out to be a circle when I all done with it. And then probably the one, if you guys ever do any like Photoshop, cubic is probably the best generalized interpolation. So when you're taking your Photoshop image and you're either well, for the most part, changing the resolution of the image, that you can select the interpolation technique, and think cubic or spline, which is roughly the same thing, are the two most popular ones. And almost looks like a circle, although actually my plot is also a little rectangular, so you're not going to get a circle anyway. Okay. All right, so now we're leaving the world of kind of data with kind of these known structures. Now we're going to go into more. I have no idea what the data is, but I want to deal with the missing data situation. So this is sort of what going from here forward is where I would, if you know nothing about the data and you need to deal with it, and you don't want to spend a lot of time trying to see if there really was an underlying structure, the assumption I would make is that it's probably MAR, and I would use an imputation technique, one of the following ones. And that's really where we're going with the rest of this topic, is just lots of different ways to explaining these imputation techniques and giving a lot of examples on different ways to do it. Some of them are computationally much more expensive. Some of them are faster, but of course the trade-off is that you probably have characteristics that you don't, that are a little less desirable. So, easiest way for imputation is to use some form of univariate imputation, which basically just means you're just going to take, if you have a column that has missing data, you're only going to use data in that column to fill in the rest. So some common ways to do this, there's the one that I would not ever recommend unless you have some really strong justifications, is the one I would not recommend is just filling it with something, because you don't know what that's going to do. And you definitely, like, especially filling with 0, you're likely to skew the mean. You're likely to, even more so than just dropping it. So that is, but I bring it up there because I know that people sometimes do that. Mean and median are a very common way to do it for numeric values. The mode or frequent is often a way to do it if you have categorical. So we haven't really talked much about categorical data to this point. Just because I think it actually opens up a huge can of worms as far as you also have to deal with encoding and so forth. We will touch on that a little bit in some of the more advanced imputation techniques, because you probably can't get away with not having to deal with it. But I'm not going to go into a lot of details because we can get mired in talking about how you encode the data as well. So. But one way they do it is, you just take if you have a missing value, you fill it in with the one that appears the most often. Okay, and then you can do a random fill. Now, this doesn't have to be like, I'm going to pick anything out of the air. You may do something a little smarter, like, okay, of my remaining data, I'm going to calculate the mean and the standard deviation, and I'm going to fill it randomly based on a normal distribution based on that mean and standard deviation. And that has actually some advantage over the mean. If you fill in strictly with the mean, you're actually going to compress the standard deviation, because everything that's missing is actually going to lie right on the mean. That's going to actually skew the standard deviation smaller. So if you actually use this random technique, you're actually going to not, you're going to still preserve sort of the mean, and it'll do a better job as preserving the standard deviation. These all work fine for MCAR, but you're still going to get the bias issues from MAR. Okay, so I think the rest of the way, we won't necessarily do a lot in terms of analysis on the different results of the imputation. I'm going to show you a lot of techniques to do them. If you want me to slow up so that you can evaluate them, I can do that as well. All right, so So mean and, so the first example here is, median will be identical to this as well. So mean imputation, the advantage of these univariate imputations, they're very fast. It takes almost no time to compute them. But as you can see here from MAR, you still end up with that problem of, let's see, what else did I? Okay, oh, yeah, the only thing, you can do the same thing. You can do the same thing with median. But you can see in both cases, there's still a significant skew for MAR. If I were to change this to the MCAR data set, is it MCAR? No. Okay, something's not right there. Okay, I guess one of the problems with trying to do this on the fly, not sure why the mean and the standard deviation are off by so much, but anyhow. What was it? Oh, that's why. Thank you. Yeah, I was filling in with the mean with the other data set, so. All right, if you did that, yeah, okay. That's a little bit better. Did I miss one on the? Oh yeah, it's actually what I was saying. The filling in it with the mean or the median compresses the standard deviation, as you can see there. So even though it preserves the mean and the median, the standard deviation itself has been affected by this technique. So even for MCAR, it still has some negative effects. Okay, at this point, let me digress for a second, talk about the libraries available. Unfortunately, Python, I don't think, has a lot of really mature libraries for imputation. The one that seems to have progressed the furthest, as far as I can tell, is a package called Autoimpute. But it is a little bit buggy, and I still think it probably needs some work. The most mature imputation packages actually exist in R. So if you really need something reliable and you don't want to write it yourself, I would suggest you might want to learn Reticulate, which is a way of running R code inside Python. But you can't, I mean, for some simpler imputations, you can get by with these packages. They're just kind of letting you know ahead of time. That's also that's also one of the reasons I want to explain how these work, so that, worst case scenario, you can write your own. It's actually not that complicated, but how if you were to write a package, you kind of have to make it generalizable to a lot of people. But if you're doing it for your own purposes, you can focus in on what you need specifically. So definitely Python has all the building blocks to do a good imputation. It's just that depending on what you need, it may or may not be there. So anyhow, since it is helpful to have a consistent imputation library, I'm going to focus mostly on using, either I'm going to use existing libraries to build up an imputation model, or I'll probably show you the counterpart in Autoimpute, just because if you're going to use one, if you force me to use a library, I'd pick that one right now. Scikit-learn has some imputation, but it's somewhat incomplete. There's only a few methods in there. And I think there's also another one called Fancy Impute. So I'm not really trying to play any favorites as far as libraries, because it's still going to, all of them need a little ways to go before they're like full service. Okay, so with that digression out of the way, here's how you would use Autoimpute to do the same thing with mean or median. So this might actually be a simpler way. Do any of you use scikit-learn's pipeline stuff? I only bring that up because Autoimpute sort of fits that model. You can, each of their models, there's a fit method, there's a transform method, and I forget what else there is. Oh, and the fit transform, which does both at the same time. This allows you to create a autoimputer or autoimputer and put it into a scikit-learn pipeline. So if you use that tool, this is compatible with that. Okay, so I did this imputed, and I can do the comparison. Look at feature A, which is what has stuff missing. And again, this was on the MAR data set, and you can see again the bias involved. Okay, we did not actually do this in the creating data set portion, but this is a data set where I created one categorical column. And I will print that, show you what that looks like. I'll explain this one. So I constructed it in a similar way to the other stuff before. So I created 3 numeric columns and a categorical column. And I clobbered the categorical one on the basis of, I forget which column, but one of the columns here. So it's an MAR mechanism, but the values are missing. And so the kind of the last fill imputation technique is, well, no, I guess there's another one here. So this one basically does the same thing, but it fills the missing one based on, let's see what was the second one. So cat C is apparently the most frequent category that appears. So basically I fill it in with, fill in with C, and depending on your level of knowledge of pandas, and mine is sort of intermediate. What this does is it computes the mode, but the mode, it turns out, is actually a list. So this extracts the top value. So if you actually ran the mode, it would actually give you a sorted list, I think, in reverse frequency order. And so the most frequent being at the top, the least frequent at the bottom. So that's just a fancy way of getting the most frequent value. Okay. And finally, this is this is what I was talking about. Instead of just filling in the mean, we're going to do something a little more clever, which is we're going to fill our missing value based on the picking the value out of a normal distribution based on the statistics of the rest of the data set, or of that column. Again, in this case, you still have, is this the, oh, this is the wrong data frame. Yeah, you still have the skew, the bias, because this is the MAR. There's no univariate imputation technique that will resolve the MAR, basically because the reason it's missing is dependent on the other columns. So if you're not using those and filling it in, you're never going to get a good result. But if it's MCAR, see if I make sure I got them all here. MCAR. Change them all to MCAR. You'll see in this case, unlike the mean that I did earlier, now the standard deviation is also kind of down in that same realm. So, you know, how I was saying how if you just fill it in with the mean, it'll tend to compress the standard deviation a little bit. In this case, by doing this random pick, it sort of fills in the standard, fills out that standard deviation. So by actually introducing a little more randomness in your fill, you're going to get something that reproduces the standard deviation a little better. Okay, so we basically covered sort of what people most commonly do in the imputation techniques. And for those of you who actually have dealt with missing data, does this sound like some of the stuff that you've actually done? Okay, and you can also see from these simple examples why for certain types of missing data, it's not necessarily a good thing. Okay, so before we get to the next section, just wanted to kind of, one question that I don't actually address here, but might come into mind is, let's say that you're trying to evaluate a method of imputing. It's like, well, how can you tell if it's any good or not? And that's actually kind of a tricky question, because when I was, I got involved with all this imputation stuff because, well, it's kind of, it's not that long a story, but my boss enlisted, who's a adjunct professor, enlisted one of his grad students to investigate this method of imputation with neural networks. I saw in that paper there was actually a way the technique could be improved a lot, so I ended up publishing a paper on the improved technique, and I'll mention that later. But in doing so, that's when I did the whole background section on MCAR, MNAR, because that was supposed to set the stage for the paper. And I did exactly the things that you weren't supposed to do that I told you not to do. Like I generated the MNAR, or the quote MNAR, in the way that I showed, and it turns out it wasn't MNAR. And, you know, so I fell through all the same pitfalls. But in doing so, really what it boiled down to, when we were working with neural networks, everything was focused on mean square error. But is that really the best measure of how good the imputation technique is? And the more I dug into it, I realized it might not be, because if you had stuff that misses the original value on both sides frequently, maybe in the worst possible way, it could actually do more detriment to the statistics than what the mean square error would indicate. So the bottom line actually in imputing, evaluating what kind of imputation technique is good for your particular application is probably to benchmark it against the particular type of model you're going to build. If you're going to do a random forest regression model with the data eventually, you may want to test random forest regressions on, you know, full data sets and then clobber them and then impute them just to evaluate in that way. Because there's no real special metric to say this one is good, this one is bad, because nearness to the original value is not necessarily the whole story. Let's just put it that way. If you're going to build a neural network model, that might be completely different, because in theory, neural networks are supposed to bring in higher order relationships that, you know, might get missed in normal statistics. So the imputation technique that's suitable for that might be something different. So, so with that, all that said, when I show you some of these multivariate and advanced imputation techniques, you know, you're just going to have to kind of keep in your back of your mind. You may want to kind of have a general feel for all of them, because whichever one works best for your particular problem may be different. Okay, so sort of the sermon on that over. The next section is actually pretty lengthy, so I want to see if you guys had any questions on stuff so far, because you may, I don't even know if any of that you'll retain any of that when you get into the next section, because, okay. So I guess the plan is let's go through this next section. If it goes long, we could take a break in the middle, but I'm thinking to try to get through this one, and then we can take another break, and you'll probably need it after this. Okay, I think this is by far the longest section I have. And I'd actually debated breaking it up into a few. Okay, start out with the same data sets, and you're going to be intimately familiar with these, the MAR and MCAR data sets. It's basically got the original data set, so we can compare some statistics against it. We have an MNAR an MCAR clobbered set and a MAR clobbered set, and in some cases, doubly MCAR and double MNAR. So I'm probably going to start saying them without, referring back to it. So hopefully you'll pick up that really we're going to primarily deal with 5 data sets here to look at. Okay, so conventionally, multivariate imputation falls into 2 categories. The first one is regression imputation, and some of you might have encountered that. The other is hot deck imputation, which might be a little less familiar. And I bring up the third one here. Neural network autoencoders, these are sort of a little more cutting edge. We're actually not getting into that in this section, but we will talk about it in the next section a little bit. This one is going to focus mostly on the conventional multivariate techniques. Okay, so this is sort of the obligatory kind of overview of all the different methods. Regression imputation, actually I got a whiteboard here. I might actually make use of this. Slide. Okay, so let's say you got column A, column B, and column C. You got data here, and data here. But let's say that this column has a few things missing. Okay. So there are generalizations for this technique when you have stuff missing in different columns, but for the most part, we're going to deal with one column missing. You'll see at the end of the section, there'll be techniques where you extend this to other columns. So one way of exploiting these columns to figure out what's here is just simply a regression. And that's what really all regression imputation is we're going to take the columns that we have full data for and use those to figure out, to guess missing values here. If A is categorical, and this, I'll digress back to, go off and talk a little bit about categoricals. That, well, the counterpart, when you're dealing with categorical values, to regression is classification. So if you wanted to fill in based on a categorical column, based on these, you might do a classification system. So, and it turns out any really can work, or can be used. I shouldn't say can work, but for regression, typically, like as in this outline here, you have linear regression, and there's also a stochastic linear regression, which is actually the kind of the counterpart of the random versus mean for the univariate. What stochastic linear regression does is it actually throws in a little bit of noise so that the covariances and the variances don't get compressed. And then I threw these out there because I don't see it actually done much or even explored. But hey, if you're going to do regression to fill in these values, why can't you use, or regressions and classifications, why can't you use any old regression So I threw in like, random forest regression. And for classification, you use KNN or decision trees. Anybody who's curious, you might want to do a little research. Who knows? You might discover one that works even better and publish it. I just find it kind of curious that that's not in any of the, at least not in any of the libraries, and it's actually pretty easy to do. So, and I think somewhere in this notebook I threw in one just for fun, because why not? You can do it. Okay. So for the, so we'll go with the linear regression first. The advantage is it works for MAR, but one of the downsides of that is that if you do a linear regression, you could actually end up with illegal values. As an example, let's say that you're using this to fill in weight, and you might actually get somebody with linear regression, get somebody with a negative weight if they're like at the very low end of the rest of the statistics. It's possible that instead of imputing 10 pounds, it might impute minus 2 pounds, which is not correct. So there's no guard against illegal values with linear regression. So to do this, I think this one is from, if you look here at the top of this, I'm kind of all over the place as far as libraries. So this kind of goes to sort of the state of imputation. There are pieces to do it from all kinds of places, but nobody really has it that well established in one place. Okay, so, all right, so what I'm going to do, this is just my way of pulling things apart and piecing them back together. It may not be the most elegant way to do things, but I will go ahead and explain it. So remember when we did our MAR construction, feature A is the one that's clobbered. So this rest is the list of all the other columns. Because basically we're going to use all the other columns and do a regression to predict what the missing values for feature A is. So, so this next data frame is basically all the ones that we can actually use for our fitting, because it has the entire data set, including feature A. So we use that, we fit based on these columns, feature A, and then we predict it by, we predict the entire data set. Okay. Okay, and I have a little note here. This is actually more when I was having some people review the notebooks before presenting it. I used this, I was told this can be kind of confusing, so I thought I'd bring in this pattern. The reason for doing it this way, number one, I can keep it into one of those method chains, which I guess is sort of the favored way of coding in pandas. But what this does is basically says assign to feature A this thing. Okay. And then what this thing is, feature A, you're going to, if it's missing, you're going to fill it with the predicted value. Otherwise, you leave it alone. I have another pattern that looks very similar to this when we talk about some of the more advanced imputation techniques, but this is what it is. And basically, it's this, except I can kind of one line it and then potentially chain something else to it. So I don't want you to get bogged down in code that looks kind of intimidating. That's all it really does, is it fills in anything that's missing with the predicted value. Okay, so that's what I've done here. And then we can do our usual stat comparison. And you see now from MAR, this is actually pretty good. This is the kind of basic percentage we were seeing with the MCAR for the univariate. So for the most part, this is good. And let's see, what's the next thing? Oh, and this was that displayer method I had shown you earlier in the helpers. The highlighted cells are the ones that were actually imputed. Probably should actually put the original value that see how it compares, but anyhow, that shows the results of the imputation. We'll probably not focus a whole lot on comparing the statistics and so forth. Otherwise, this thing could be in another 3 hours. So I'm going to go mostly on just explaining the methods. I guess we'd leave it as an exercise to the reader if you want to delve into any of these and pick apart its statistics and its properties a little bit later. Okay, now the stochastic regression basically, I hope I'm using the term correctly for any of the statisticians here, but the residuals are the difference between the predicted value from the regression and the actual value, right? So what we do is we take the residuals, we're going to assume a normal distribution in this case, and we're going to then generate noise based on that normal distribution and then add it back into a regression. So what it does is it does a little bit better job of simulating the variances, but it also still has that same pitfall of creating out-of-bound values. So first step here is we're going to calculate the residuals as well as the mean and standard deviation. I guess if you want to see the mean, you need to cluster them together. So this one is pretty close to zero mean. And then what we're going to do is we're going to add this noise to our predicted value. So this predicted value is the one that we generated from our linear regression before. And we can do the usual stat comparison. What was it? Was it pristine? DF and imputed. Looks like I misspelled pristine. Is that not what it was called? Oh, let's call it DF. Oh, in the column. All right. Again, pretty good. I think the standard deviation is even better here. If we were to go through and do the whole covariance thing, you'll probably find that that actually matches better to the original than even the linear regression version. I don't know if you guys want me to slow down so that you can play with these anymore, or just want me to move forward. But originally, when I was developing the notebook, I'd run all kinds of statistics on each of these. But that can be somewhat of a rabbit hole, and it turns out this is, as I said, this is a pretty long notebook to go through. Okay. They actually call the linear regression in Autoimpute least squares. So got the least squares imputations, and also the counterpart to the stochastic is this one. So then we can analyze the results. And I generally won't go any farther than this in the rest of the analyses. Just column again. And then we can look at this. This actually might be better. We can get a better idea of how the stochastic compares. Yeah, I think the main significance in this is that you can see that standard deviation in the predictions is better if you add in a little bit of that noise from the residuals. Okay, so the last thing is sort of this regression section. When I was coming up with this, I just said, you know, all this really is a regression. We're taking the existing columns we know about, and we're predicting values based on what we do know about A, the relationship between A and these, and then just filling in the rest of the data. So I said, you know, in the class on machine learning I teach, you know, the two regressors that we use that's in the curriculum are you know, linear regression and random forest regression. So it's like I thought, well, why not? Let's just do it for the hell of it and see how it goes. So this is basically the same pattern. We're taking the data that we know, that we have full knowledge of. We're using that to make, to fit a model, and then we're going to predict the rest of the data set from the missing, to fill in the missing values. So I guess this one takes a little longer, the random forest regression. And okay, so now that we've got the predicted values, we're only going to fill in based on the prediction of the, only fill in the missing values. We're not going to replace values we already know. And let's do the comparison again. I think we call that one imputed. And, you know, off the bat, it's actually not bad for standard deviation even, so who knows? I mean, and I'm sure if you go through, you know, the scikit-learn package or any of the others, there's tons of regression methods. And to be honest, I don't know why people haven't tried others. You know, and who knows, maybe that's a good survey paper to come up with, is just try different different regression techniques for imputation and see how they work. So I couldn't find any papers on it. I'm not even when I was in grad school, I was not very good at doing literature searches, so I could have missed a whole bunch of stuff. But, you know, you know, at least in the few hours I spent looking, I couldn't find anything other than linear regression for imputation. So, you know, coming kind of from the world of playing with artificial neural networks, it was like, you know, why not even try an artificial neural network to get that? Will you get better results? Who knows? Never tried. So, so if you want something to play with, you know, copy this pattern, look up all the different regression techniques in scikit-learn, come up with a summary of which generally does better. Okay. So far the categorical stuff has been sort of the stepchild of this talk, so we'll at least talk a little bit about that. So the counterpart for categorical variables to regression is classification. And I always found it kind of funny, but you know, sort of the rudimentary basic method of, or the one they teach first anyway, of classification is called logistic regression, right? So I always found that kind of interesting, the misnomer that a regression classification algorithm is actually called a regression. But with that said, that's what we're doing. Okay, so we'll load this categorical variable. Oh, I guess this piece of code is buried in there, but this imputation displayer, what that does is it figures out what's missing and then sets up a style sheet in your pandas data frame so that when we display it using the display any data frame with the displayer method, it'll highlight the values that were actually imputed. So that's just it's a useful little tool to see what work has been done. Okay, so logistic regression. The only thing that is a little different here is that, or do I use it here? Maybe I don't. Oh, I don't. This line is extraneous. Because actually, I believe the scikit-learn logistic regression module handles categorical values without actually having to encode them. So I believe that line is extraneous. So this is just basically the same pattern. We calculate, we do the prediction, bad variable naming, but we predict it and then we fill in the missing ones. And so this is actually, gives me, I seem to remember that we imputed with the most frequent value, and that was category C. And in this case, here it puts cat B, cat D there, and I'm sure other places it'll put in E as well as C and A. So again, there's probably a huge universe of classification algorithms. As far as I can tell, no reason you can't try them. But this is the tried and true one that they use in these imputation packages. Autoimpute also has that in there. I just did not incorporate it because its handling of categorical variables is a little bit dicey. So, but again, all this stuff can be done with, if you understand the underlying mechanism, you can do it by hand, and it's not that hard. Okay. The other major way of multivariate imputation is called hot deck imputation. So basically, well, actually, let me draw it. So, all right. So basically what you do is, let's say we're going to impute this value here. Based on some kind of metric of these values, we're going to pick a set of what they call donors. So let's say, it's these three things, okay? And we're going to do that for every missing value. So this algorithm is a little more computationally intensive because you're going to be doing it, it's kind of like doing it one at a time. But of these three values, we're going to pick based on, it can be straight uniformly random, or it could be some other random based on how close it fits the metric, whatever. You're going to pick one of those three, and then you're going to, let's say it's this one, and you're going to just fill that value in. Then you're going to start the whole process over, select three more donors, could be the same one, based on whatever your criteria is, and randomly pick one of those to fill this value, and so forth. Now, the advantage of doing hot deck imputation is that you never get an illegal value because you're picking from already known legal values. So in the case of, you're not going to get somebody with a negative height or, or for that matter, someone with a 0 blood pressure. Okay, so the easiest way to demonstrate this is probably with Euclidean distance. So I took this is sort of the data set that, I think this was actually our MAR data set, but I only took the top 10 because I didn't want to, we're only going to show sort of one iteration of this. Okay, so since I'm going to do the Euclidean distance, I'm going to apply this method here called distance, and now our demo DF looks like this. Okay, so the distance here, so what we're going to want to do is select our donors based on this Euclidean distance. So this is basically, so what I mean by Euclidean distance is, okay, from this point, based on the remaining features, what are the closest points? So actually, just by eyeballing it, number 8 is the closest to number 7 as far as Euclidean distance, 0.103. Okay, so that's what I mean by, based on distance. Okay, so the remainder of this, okay, so this is kind of described in this paper by Van Buren. Link is here, also in the reference section. Okay, so method 1 is, the simplest one is just pick the one that's closest. And so, like I was saying, number 8 is the closest because 0.013, so 2.74. So what we'll do is we'll just take this one and fill it in there. That's kind of the quote unquote method 1. The second method is pick all the donors under a particular distance threshold. So we'll do this. Okay, so we've set 2 as our distance threshold. So our donors will be selected from one of these 5. And this is going to be some kind of random selection. So if you run this again, you may get a different value. Okay, a lot of these imputation techniques have a stochastic nature to it. So if you run it again, you're going to get a different imputation. And that's actually a useful fact, which we'll mention later when we talk about multiple imputations. Okay, so here we go. The third way is just pick the 3 n closest values. In this case, 3 is actually, if you look at some of the software or packages out there that actually implement this, 3 is actually, they use this method and the default is 3. So in this case, again, 8, 6, and 5 are the closest. So we'll pick fill in one of the values from those 3. The fourth method that's mentioned is you're going to consider this one is a little different. You're going to consider all the donors as possible values, but you're going to select the one inversely proportional to the distance. So that's the one that's, so it's possible to get any of the values, but you're going to get a different one. And since this process is different every time, and it's integrated with the donor selection and the random choice are integrated together, I don't have the fun little table. So in this case, this value got picked, which is, we can probably go back to the table and look to see which one that is. 2.5. Yeah, it looks like it happened to pick. Actually, did it pick? It's either picked 1 or 5. Picked 1, so it just happened to pick Now, if I run this cell again, it's going to pick a different one by random chance. Okay, that's the overall principle behind hot deck imputation. In principle, they do not use Euclidean distance as the metric. The most common hot deck imputation technique, and fortunately this is about as deep as we're going to get into this category, but it's important to mention this because this is what is actually used, is this method called predictive mean matching. I'm not quite sure how this name correlates with the technique. I don't know where the mean comes from, where the matching comes in, but that's how it's termed. Okay, again, we'll load this demo data set. All right, this one is a little more complicated. I think I'll run the cells first until I get a picture. All right. So the metric is you do a linear regression you do the linear regression prediction, and you get the regressed value, and then you're going to select the donors. We're going to use the n equals 3 version. And we're going to pick the donors that have a regression value closest to the predicted regression value. So that seems a little convoluted, but that's what the algorithm is. If you actually look at if you're a statistician, you might be interested in some of the other options. There are all kinds of things about prior probabilities and stuff like that, which I don't really understand. And so for the most part, I leave those on default values. But the underlying mechanism is this. So the donors will be from those are the 3 closest distances. So our donors will be selected from these 3 values. And again, this one is actually seems to be very computationally intensive. So I truncated the Autoimpute version. Autoimpute does the full-blown version of this, which probably incorporates other options, which I have not accounted for in my demonstration. So if you run this one, it actually, even at 100, I truncated it down to 100 rows, it still takes a fair amount of time, which you'll see. And actually, I'll go ahead and run the next cell, and you can see what is okay. Well, I mean, you can leave it running. Yeah, I did notice this one takes quite a while to run. Does a lot of stuff. I'm not sure why. It may just be because the example I gave is a very special purpose, focused solely on the objective, whereas these probably have to accommodate other parameters, which is why it may take longer. But this is actually from what I understand, for sort of a lot of the imputers, this is the default algorithm they use. And one of the reasons why I did not have time to really investigate it on these data sets, but it appears that if you have more than one column missing, with data missing, linear regression at least doesn't really work that well. And predictive mean matching does. And I'm not, even for MCAR. So now, I'm not sure if that's actually completely true, but when I tried it out, that seemed to be the case. Yeah, this is going to take a little while. Okay. Well, while this is going on, do you guys have any questions on what I've discussed so far? Is it comprehensible? You guys have been kind of quiet, so I'm just kind of wondering if you're all still with me or not. It's So this is one of the reasons why, okay, so it's done. It took a couple minutes. Actually, some of the stuff subsequent to this will actually also take a little bit of time. So you can kind of see what it's doing with the imputation. If you want, you can do the usual comparisons that we've been doing all along. To be honest, I mean, I'm sure for you guys as well, it gets, you know, if we keep doing that every time, it's going to get really dry. But if there's any particular technique, you know, you want to dig into, I mean, you certainly can get these, you have these notebooks, so you can try them out on your own. Okay. So that's sort of, that's actually one long section. Do you guys want to take a short break, or you want to keep and then break after that? Break? Okay, yeah, because I know after a long thing like that, you might need a chance to let your mind settle. So we'll go for another 10 minutes. We're actually on a good pace. So the next technique, this is actually more, you know, we kind of just talked about univariate versus multivariate. This is a technique that builds on top of it. This is the sort of, has been the gold standard for imputation for ages. Only recently have there been implementations in Python. Autoimpute has one. It's a technique called mice. And it deals with the case. So far we kind of made things easy by saying that there's only one column with stuff missing. But realistically, right, you're going to have A, B, C, D, E. And then you'll have stuff here, stuff here, stuff here. And if you're not lucky, you're going to have some stuff missing here, missing there, maybe one missing there, a couple missing there. So that's probably a more realistic situation. Well, you're probably going to have a few columns that don't have anything missing, but this is more real world. So far, you know, we've just kind of confined ourselves into one. And that's really good for explaining the concept. But now we're getting into sort of, well, all that's nice, but this is what I get. So what mice does, and sort of the optimal version of this, is that you sort the columns by how much is missing first. So let's say that column E has the fewest. Actually, the first thing you do is that you impute each of these columns using some form of univariate imputation. You don't really need to get fancy with the stochastic imputation. Quite commonly, mean or median works fine. So you fill them all in with sort of your first cut at an imputation, which you know, mean. Well, basically, it's mean for numeric data and mode for categorical data. Okay, then you take the, so what you do is you take, I got it backwards. You take the column that has the most data missing, and then you go ahead and delete the values that you just imputed, and you use the rest of this to do some kind of imputation to fill this in. So your first pass will revise this imputation based on everything else. Now let's say column B is has the next most missing stuff. Then you take A, C, D, and E based on these imputed values, and you fill in that. And you just keep doing this until you get through all the columns that have missing values. Okay, so that's sort of your first iteration. Now you just repeat the process. You go back to A, and you refine the imputation on this based on the new values you impute. And because this is sort of that kind of iterative process, you stop when you basically are satisfied with where you've gotten. And that may just simply be that these values don't change much. There is a danger that sometimes these go cyclic and you don't actually stop, because you know, it may go to, say, 0.1, then 0.2, then down to 0, and then 0.1, 0.2, just kind of So there's always that kind of risk. So at some point you may have to look into it and say, that's enough. Most mice imputers have like thresholds and stuff that'll keep it from going on forever. And you can also set thresholds for saying, when it starts changing by this much, I'm saying it's done. So mice is sort of this iterative process, which also means that when you impute each column based on the other, you can choose your technique. I think by default, mice uses predictive mean matching, which we just kind of finished talking about. And if you tell it it's categorical, I think it does a multinomial logistic regression for categorical values. Again, we're kind of, for these demonstrations, we're going to sweep categorical data under the rug. But, if at any point you want to get into categorical data, I will post some contact information at the end, and, we can talk about that. But just categorical data also involves encoding as well. And so you get into a huge can of worms there. I kind of mentioned some of them at a very high level, but you don't, but we purposely don't go into, a lot of these data sets purposely are numerical just because I think it would tend to confuse what I'm trying to demonstrate. So here's kind of what I was saying with this. The reason I use the MCAR set here is just because for my iterations, I'm going to use linear regression, and for some reason I think linear regression, when there's missing data, doesn't really work as well on MAR missingness. Predictive mean matching is what you actually want to use in that case. Okay, so step one, as I said, I used a univariate imputation, and just to be different, I used a different one. If you recall, our double missingness variables only clobber feature A and feature B. So we don't need to go feature B, A, B, C, D, E, because D and, C, D, and uncorrelated don't have anything missing. So in this case, just to be different, I did column A with mean imputation to start, column B with median. No particular reason, just wanted to show that you could use either of those. Because this is already, this is an iterative process, the starting point isn't super important. You don't want to pick 0 because it's just too far away from where it should be to start with. But any of these techniques, you don't need to go through the elaborate mechanism to do a normal or random imputation. You can just use mean and median. Okay, so that's what happens in the first iteration. Then we impute feature A based on the other columns. So this shows what values got imputed. And then the next step is to just repeat the same process. Now we're going to impute column B with everything. And note that so this shows all the imputed values now. But you can note here that column B also used the more recently imputed value for column A, as well as C, D, uncorrelated. Actually, as a side note, because we actually know the uncorrelated column is uncorrelated, it really is of no use in helping to predict the other columns. So if you actually know it's uncorrelated, you don't need to incorporate that in your model, and that may simplify things. I was just lazy. I didn't want to drop it. But it doesn't really do any work because it doesn't provide any information about feature A or B. Okay, and now I put both of those. Now I'm going to do A and B again. But I'm going to kind of put them in the same step. We get this result, and then we'll do our usual stat comparison. And for this double MCAR, it's pretty good. Again, I'm doing a lot of eyeball testing. It's like for 8,000 missing values out of 20,000 rows, having a bias under 1%, pretty good, right? You got close to 40% of your rows are affected, and you're only skewing your data by less than 1%. View that as pretty good. Okay, so just for completeness, if you wanted to use that Autoimpute package, it does have a mice imputer that pretty much does this. This is the case where having the package actually is helpful rather than building it yourself. You saw how cumbersome it was for me to do that. I could easily have put that into a loop and run it for X number of iterations to get the result, but this does it all for me. Again, I'm doing the least squares just because the predictive mean matching kind of takes too long for this. And so, I'm not sure if I got the exact, well, it probably didn't get the same results as before because this thing ran through as many iterations as it needed until the default termination criteria was met. Because I didn't specify any of the parameters for, how long to run, what the thresholds are. I just kind of left it up to the imputer. But again, like with using any software package, always look at the parameters and the options. Sometimes sometimes you'll look at the defaults and say, yeah, that makes sense to me. I'm going to keep those. Other times they may not. Has a ton of options, and it could spend an hour going through them all. But if you actually use this, read it on your own. So, I mean, I'm probably not giving mice enough. Doing justice to mice because it actually is sort of, this technique is sort of the gold standard by which you should impute data. And it has, and quite often people just use the default settings and it seems to work fine. I believe, like if you look at publications on imputation techniques, almost all of them will make a comparison to mice because it's just been the thing that's been there forever. And it's really what the yardstick by which other imputation techniques should be compared to. And if you're actually doing a research paper and you're comparing an imputation technique to mice, you might even want to run the R implementation because that's probably what most people are referring to. But it can be done in Python, and this is the way you do it. Yeah, and actually one thing I kind of glossed over if you were actually paying attention to the code. When I did the mice imputer, there's this kind of strange little indexing I was doing here that I kind of glossed over. It turns out mice is usually implemented using what they call a multiple imputation. So what this actually resulted in was actually an array of imputations. And so in order by setting these parameters here, I'm actually just saying do it only once. And so I'm just getting the value for the one imputation I did do. But in the other advanced technique that closes out this section, it's called multiple imputation. And this is why I mentioned it here. So before I move on, any questions on mice? Because I think, you could probably get by not knowing anything else if you figure out how to use mice. It may not be the best overall because people are coming up with newer techniques, but it's the one that's been around the longest, it's the most established. And, with all that, probably for any research that you need to apply it to was probably the most unassailable technique. So anybody questions on mice? All right. And actually, there are also even some good, I actually did find some good blogs explaining the basic technique. All right, so multiple imputation is really, in some of our imputation techniques I mentioned above, there's actually a stochastic element to it, right? The hot deck imputation, we're going to select donors, but we're going to randomly pick from those donors. Stochastic linear regression, we're adding some noise to it, some random noise. So every time we run the imputation, we're going to get something a little different on some of these techniques. So what multiple imputation essentially is you're going to run that same imputation multiple times. And so instead of getting a single value for anything missing, you're going to get a set of values. Now, why that's significant, and this is probably more applicable to the statisticians, is that if you actually get it, it's more like, rather than filling in this value, you're filling it in with almost like a probability distribution of what that missing value is. And you can carry that forward into other statistical analysis. Personally, my background is much more, my mathematical background was much more the theoretical, so I liked everything crisp and not uncertain. So this always kind of bothered me a little bit, but if you carry it forward, you can do things like, you can incorporate this kind of fuzziness in the value into your error calculations or your confidence intervals down the road into your model. So you can actually incorporate it. So it provides a little bit more of a statistical result for the imputation rather than a single value. So that way, in your final result, the fact that you don't know this value, but you have a good idea of what it might be, can carry forward into maybe increasing your error margin or your confidence interval in your final result. And so for those of you that actually deal with that in statistics, that should be useful. So to do this, Autoimpute has that as actually a feature as well. But even if you don't use Autoimpute, use some other imputer, if it has a stochastic element, you just run it 5 times or 7 times or however many times you want. Okay, so this is sort of what the raw output looks like from Autoimpute. And so this will explain why I had that weird array notation in the previous section. Okay, so it produces, in this case, we have 5 imputations. So it produces a tuple where the first element is basically indexed to count which one. So this is the first imputation, second imputation, third, fourth, fifth. Second element in the tuple is a data frame. So this is the entire data frame with the values imputed. And you've probably seen if you actually print a pandas data frame rather than having Jupyter render it, it looks kind of ugly like this. But so that's what the return values look like. Okay, but I did note up here, here, that the least squares option, doing a least squares fit for regression is actually deterministic. You do it twice, you're going to get the same answer. You do it 5 times, you're going to get the same answer. Okay, so that's the imputed value. So we can see like number 1, feature A, row 1 is imputed. So if we look at what that looks like when I did this, it's linear, linear least squares regression, get the same answer every time. So in effect, it's kind of useless to do it on something that is completely deterministic because you got no statistical variation there. So, so really the rule is for multiple imputation, if you're going to do multiple imputation, you need to do some form imputation that has a stochastic element to it. Okay, so we'll do the same thing, but now we're going to use that stochastic linear regression. So this is basically the same as the linear regression, except we're going to add random noise based on the residuals of the linear regression. Okay, and if we look at this now for that imputed value, we get something missing. Not missing. We get some variation. Now, based on even these 5 values, you can compute a mean and a standard deviation for that missing value. And that presumably you can carry through onto your model and incorporate the fact that's missing, but you have an estimate for it. So this is why you would use multiple imputation in any kind of statistical modeling that you'd build, because it actually enables you to kind of carry into your statistics and your final result any contribution based on the fact you actually don't know what the value is, but have an idea of what it might be. Okay, so to summarize this, okay, so any questions on multiple imputation? I don't know that, yeah. I think it's probably highly dependent on the model you're using, how it carries through. And as I said, I'm not that much of a statistician, so I don't know exactly how it carries forward. But from sort of my minimal statistical background, I can see how right there I got error bars, right? And so I can use that to sort of carry forward, and any calculations I do subsequent to that, I can incorporate the error margins in there. But I'm sure, if you got deeper statistical background, you can probably find more ways to incorporate that. Yeah. So it can incorporate the uncertainty from here. Okay. Yeah, so certainly if you have models that account for uncertainty, this would be very helpful. Right. So like you were saying, that model. Yeah, so those you could actually see how those are tied together. So that's good mentioned. Okay, and really that's the key point of certainly the multiple imputation is much more useful to those people that have to be much more concerned with the statistics of the model. All right, so basically univariate imputation, if you know the data is MCAR, it's the fastest, quickest, easiest way to deal with it. Multivariate, really you got the regression classification, which is sort of the simplest way, and then hot deck imputation is actually has the advantage that you're not going to get illegal values. And then based on those building blocks, you can do mice, which is really it's actually great for dealing with missingness patterns that are beyond just a single column. And probably the one thing that, if you don't take anything else from this talk or workshop away, just remembering that mice is really what you want to probably use if you don't have a clue about how you want to deal with the missing data. That's probably the safest bet. Methods like dropping data or filling it in, they're fast, but they have a lot of problems. Mice tends to have the fewest. And then multiple imputation is a way of actually incorporating the uncertainty of your or representing the uncertainty in your imputation into your model itself. All right. So getting down to the home stretch here. All right. Do any of you guys here work with artificial neural networks? Because this is sort of now I mean, I like to play with artificial neural networks. I don't really need to do it for my job, but I find it quite interesting. Actually, when I was in graduate school long ago, when this was all really new stuff, that's when I was first exposed to it. But it's kind of made full circle. It's now the hot thing again. So, not to date myself, but I was doing this in the 90s. So I'm kind of, I still have fun playing with it. So this is sort of like, and part of the reason to see how many of you are out there is before I start insulting you all. Because there is certain casualness with some of the data handling when it comes to the neural network people, especially with regard to the statistics. In fact, I'll tell a little anecdote. Because of COVID, I have a friend up in the Bay Area that goes to these frontiers of AI, meetup type thing. And because of COVID, I don't live in the Bay Area. He invited me, and I went to a couple of these. And during sort of the networking part before that, someone was asking, how do you deal with unclean data? And there was a guy, I think he worked at Google, and he said, "Oh, don't use unclean data. Just go get clean data." That's sort of been kind of the attitude I get from some of the people that are really into neural networks. And we'll just find a nice curated clean data set. Well, that's great for those of you in the ivory tower, but those of us in the real world, we have to deal with unclean data. So, and in neural networks, there's a lot of speculation on how things actually work internally, but nobody really knows. So, and I'll be describing some of that theory behind some of this in this section. So, first thing is, we'll stay on the imputation line for a minute, or a few minutes anyway. This is also where some of the stuff will run slower, because I actually have some small, but I guess there's really no such thing as quick neural network model training. But the first category is the use of, you can actually use neural networks to impute data. So this is actually the paper that my boss had a graduate student investigate for us. It uses something called the denoising autoencoder. Now, autoencoder, for those who might not be familiar with the term, is basically a model that predicts where the inputs predict, the output that is predicted is the same as the input. The theory is, and this is sort of where that hand-wavy neural network thing comes in. The belief is that the neural network learns the structure and the missing values are just kind of noise. So it will eventually learn to what the true structure is and ignore the noise. Whether it really does that, but that's sort of the mindset behind autoencoders in general. And so the denoising ones they believe that eliminates noise, and they treat the missing values or the deviation of the, because neural networks, you have to fill in a value. So they start out by imputing with the mean. They treat the deviation from the mean as noise and hope that the autoencoder figures it out. Okay, so, and actually it had been a while since I've done this. So when I was doing this notebook, all the predictions were really bad. And I realized the reason is the data needs to be scaled to work properly. So I'm using scikit-learn standard scaler here. And this restored df function is really just the inverse of that scalar, so that when I'm done scaling, I can get back to my original values. Okay. Oh, yeah, this is one of the few places I start actually putting in diagrams. But it wasn't until the 6th slide I figured out the way I wanted to to do it. Okay, so this is, for those of you, well, if you're not familiar with neural networks, let me know, I'll slow down. But they basically have layers of, they call them neurons. And the basic architecture of this autoencoder, you start out with n, which is a number of features you have. And then the next hidden layer has n plus theta, and theta is a hyperparameter. And in the paper here that's cited, theta is 7. Why 7? They just said that works best, so I stick with that. Then the next one has increases the width by another theta, and then finally the middle layer has basically an extra 3 theta version. Then it kind of gets smaller until it's back down to n. So it kind of grows in the middle and shrinks back down until it's back down to the same. So basically the way you train it is you feed the predicted value. You feed the ground truth is the same as the input, if that makes sense to you. So basically, okay, so I guess if it doesn't make sense, let's see if let me go through it, and if that still doesn't make sense, then if you have a question, we can kind of slow it down. So the first thing we do is we will impute it, the missing data, with a univariate imputation, in this case median. And it's the same, in his paper he cites mean or median or most frequent data in the case of categorical. And again, just to duck the encoding issue, we're just going to stick strictly to numeric. Theta is 7. All right, here we split the data into a test and training set. Okay, and then here's our Keras model using TensorFlow. You guys do neural networks, you use TensorFlow or PyTorch? TensorFlow, okay, good. So we build this model, and apparently this library has some, I think the error message as you come here is trying to use some graphic accelerators to speed things up, which aren't available. Yeah, and yep. And actually the Docker image I have supplied, it actually intentionally doesn't, so. Okay, the thing with the way these TensorFlow models are, once you kind of declare its structure, you compile it, use a particular optimizer. These days, I think Adam, and I forget what it stands for exactly, adaptive something, is kind of the most common one. That we won't get into any like the nuances of the neural network itself. I've just picked, those of you who dealt with neural networks who know that there are tons of hyperparameters. I just picked a bunch that seemed to make sense. Also, for those that are familiar, they say that the hyperbolic tangent is actually a better activation function than the rectified linear, which is actually the one that's used most now. So that may not mean much to the rest of you, but okay, this next cell will take a while to run. And I'm only running 50 epochs. If you want to actually see the progress, you can get rid of the verbose as false and just let it run, and it'll print a nice progress graph. I suppressed it because later on in the enhanced version, they also, and then, and we're going to use mean square error as our criteria because we're doing strictly numeric values. That's actually where another potential can of worms can open up, is when you start using, okay, it's done. When you start using categorical values, then you may want a different metrics for the loss function. And so for those of you who are familiar with neural networks, this is sort of the progression of the loss function as progress goes. We only ran at 50 epochs. It might go down a little further if you go farther out. Okay, so that in a nutshell is this autoencoder technique. Oh yeah, I guess the final thing is we fill it in. And did I do a stats compute? A stats comparison? And I forgot what I called the data set. It's DF. Oh yeah, I found that there's actually a pandas method that will fill in if something is actually missing. I actually, it's called combine first. It's kind of a fun, it's actually a useful function if you're going to build your own imputation. What this does is, on this data frame, SD df, if this has a nan in a spot, it's going to fill it in with this corresponding value from this data frame. So that's actually, especially for these neural network ones where you get entire data frames back instead of just a column, it's actually a convenient function. I kind of wish I knew about that when I was actually doing some of these autoencoders a couple of years ago. All right, so, and that's imputed is the name of the data frame. And since this is a couple columns, we'll look at feature A. It's not great, but but you know, I did not tweak all the hyperparameters. I just threw down some that made sense. I just wanted to demonstrate the technique. You can do some others. From a displayer. Yeah. You can also do this to just show you where the you can look at the entire data frame. Oops. Okay. Oh, how many rows do I want to show? Yeah. So that's what it did to fill in. Okay. Yeah. That's probably more to the fact that pandas NaN is actually always a float. So if you have an integer column, it's going to coerce your column to be a float, and then you may have to convert it back to an int if you want to enforce that. Yeah, there's a bit of type. That's one problem with, I think it's actually a NumPy problem at the end, that there's no NaN that's an integer. And so if you're actually going to try to use, yeah, so, and that, you'll see, I'm not super careful with that through here. But yeah, okay, so those are good points though. But in this particular context, the combine first actually works well, because all the neural networks always generate floats, and the predicted, the second one has no nans in it. Okay. All right. I'm not going to go into this one in a huge amount of detail, but figured I might as well cite my own work as well. This is I did about 2 years ago. The link is here. And it follows the same kind of methodology except what I do is, let's see, what's the best way to describe this? So what I do is I have my neural network, and I train, so it's an autoencoder, so I train it on X, but after a certain number of iterations, you get an X with imputed values, so let's just call it X1. Instead of just saying that, I do it far less than I do for the autoencoder in the first case. But then, instead of stopping, I actually then use X1, and I train it again. And then after one or two iterations only, or epochs, I go through and I take revise imputation and do the whole thing again. So in a way, it's very mice-like in that you revise the imputation and kind of go through this process. Because I found what happened with the autoencoder is that if you impute with the mean, this method will tend to still try to pull your imputed value towards the mean. So if the mean was actually a bad guess for your value, it's going to still try to influence it back towards the mean. Whereas this one will allow the value to drift a little more. So that if the mean was actually a bad initial guess, it would come closer. So, so this sort of was saying in this cell here, this is sort of the initial fit. We only go through, the previous one I went through 50 epochs. I'm only going through 10 here. Okay, and then subsequent to that, I'm just going to do a bunch of 2 epoch states, but I'm going to revise the imputed value that I feed into the autoencoder. Now, it turns out in my paper I do another thing where I actually modify the loss function so that if the value is actually missing, I don't use it in the loss calculation. But that's actually rather complicated to do in TensorFlow, and I didn't want to digress down that path. But if you actually look at the paper, that's explained. So what I've done here is just to show you one iteration in this cell. Finally, in this cell, I do the other, how many times? 19 iterations. So all in all, I'm doing 50 epochs as well with this technique. It's just I'm allowing it on after 10, because you can see in the original learning curve, the error rate, the loss function drops sharply. And by the time you get down to 10 iterations, it's practically, you're fine-tuning at that point. So this basically, you can think of it as a very coarse training and then a bunch of fine-tuning, revising the imputation in between. Okay. Yeah, so we're getting down to our last half hour here. Right, this is over at 12, right? Yeah, okay. I'll let this run and I'll, okay, so you can kind of see here, sort of this is the, I don't know if this is really very telling, but the basic thing started here, and then at this point I'm fine tuning. It turns out, at least from the examples I tried in my paper, it actually was surprisingly better at preserving covariant relationships as well than the autoencoder that was in the first paper. So we'll go through this, and then you can display. Since we are running a little bit shorter on time, I'll just I'll leave it up to you as an exercise if you want to. To analyze the relative merits of these techniques. Okay, the final thing, I think, let me just make sure that's the final. Oh yeah. Okay, so this is sort of the general process behind machine learning, right? You train the data, and then you test it. You train the model, then you test the model. The part that sometimes is overlooked is that, okay, you got your model built, but beyond that, you're actually going to use it So there may be data coming in that's subsequent to your initial training and test set. So there's really 3 stages to a machine learning model, which is train, test, and then once the model is established, you're going to still use it. So how do you incorporate imputation into this pipeline? It's pretty much simple. As long as your imputer, all these imputation mechanisms are models. As long as you can save them as you save your pipeline, you can just stick it into your pipeline. So this is sort of what I demonstrated here. And so this is a wine quality test set that I got from the UCI data repository. It's just one of the few that had a lot of numeric values, not a lot of categorical. Okay, so this is a typical scikit-learn pipeline, just doing a random forest regression on it. So basic thing is that we're going to one-hot encode our type column, which is actually, since when we're running out of time, I didn't display the whole thing, but basically all the features are numeric except for the type, which is a categorical, and it's the type is red or white. Okay, so we'll do the one-hot encode on the type, and then we're going to scale everything and then pass through the random forest regressor. That's your standard way of building a model. Your pipeline will be something similar. You might have additional cleaning steps. And so we'll run it, we'll get our result. That's building the pipeline. Then we can test it. Oh, sorry, hitting the wrong button. So it's, that's score of 53%, not great, but anyway, this is just more about demonstrating what you do. Why am I clicking the plus? And so this is sort of the, what you might do to predict at the end. So all you do, you can incorporate, and Autoimpute provides the imputer. One note here, there's a Panda hack because some of the scikit-learn pipeline stuff generates NumPy arrays and not pandas data frames, and Autoimpute requires panda data frames. So these Panda hack transformers, all they do is they label the columns so they can make them into a data frame. Okay, so this is really just showing I'm inserting an imputer into the same pipeline I might use for training. These data sets actually have data that's been clobbered, the wine test, and then after the data is trained, you might still get data to fit into, when you're using your model, you might get data that also still has data missing, right? Now, it's not like you're going to train on imperfect data and then get perfect data after the fact. So if you incorporate the imputer into your pipeline, you can make predictions. So this is sort of simulating. I got my model all built. Now I want to predict these new values that are rolling in later. So that's what's going on there. Okay, the last topic in this section really is, and I apologize, I am kind of speeding up the pace because we're getting shorter on time. But be happy to talk to any of you about this if I've glossed over something. Okay, so now you got kind of 2 different worlds here, especially with neural networks. Okay, let's say that I've got missing data. Now I want to actually use multiple imputation. Can I use multiple imputation with artificial neural networks? Right, because it almost seems like the concepts don't connect. Well, one approach is to you can kind of fuzzify the imputed values by just augmenting your data set by just stacking them together. So I can take the data set and impute it 5 times, and then that's my data set. It's going to be 5 times the size it was originally. But for the missing values, they're not going to appear the same every time in those 5 versions. And I'll use that as my training set. So that's one way of doing it. So here's the code here. So basically all I've done here is I've stacked the data frames all on top of each other. They're concatenated, so I have 5, or I'm going to here. So I got 5 copies of that data frame. I whipped up a quick TensorFlow model to do the classification. Turns out the wine quality data set, the quality column is really just it's a numeric value, but it's considered categorical because it's how do you rate this wine from 1 to 10. Okay, so I'll run that and I'll get my quality. I'm fitting the model. This is done really short because only 10 epochs. Because I don't think this is actually, at least the model I selected isn't, because it's so small, it doesn't do a good job of classification, great job of classification. Yeah, so it does. Okay, so now we do that, then it's like, well, how do you test it? You can do it testing in a couple ways. Your test set, even if it has imputation, you don't necessarily have to like do the stack. You could just do one copy. You could actually test it by doing all of them. I'll skip over here. Same thing when you get a new value, a future value coming in. If you do a multiple imputation on that using their imputation models, you could either just take one of them and just do one imputation and ignore the rest, or you could do some kind of combining, like do a majority vote in this case. So I will skip over running these because I don't know if they. Well, actually, I guess I can run them. These don't take long. So actually, it turns out in either case, as you see, in the first case, I only picked the first imputed value, and the second case, what did I do? I combined them together. In both cases, it came out with this for the same value. It came up with 7, so it didn't matter for that particular line. Okay, another way is to just train multiple models independently, one based on each imputation you do. I should add that I had not seen any of these things really applied to neural networks. These ideas actually came from other types of machine learning algorithms. They do for random forests and stuff like that. There are a few papers that do this to incorporate multiple imputations. So what this does is I basically am running 5 models, and each one will produce a different result. At the end, how do you combine them? You can use one of many ensemble techniques. I'm sure if you're familiar with machine learning, especially in the random forest and boosted tree world, there's a lot of ensembles for combining models, the results of models. You can use one of those techniques. And again, we can do our aggregation. Again, for that particular value, I get 7. So all these techniques have been equivalent in my limited case. The other thing that's just worth mentioning, because I've seen this method in the literature, is bagging, which basically what they do is they do a bootstrap sampling, they do a single imputation, and they feed it into a model, and they do some ensemble at the end. I won't run this code. but you can certainly run this at your convenience if you choose to. Also worth mentioning, you can also define the actual missingness as a feature. So, back in the world of neural networks where you just kind of throw everything into a bucket and hope it figures it out, throwing the fact that a particular column on these features is actually missing or is imputed gives it more information. And so maybe it can incorporate that missingness into the model. This definitely works they do this a lot, definitely in decision trees. Haven't seen it in neural networks, but just another thing to throw in there. Maybe you decide, this is just too heavy-handed for imputation. I'm going to let my neural network sort it out. I'm just going to do a simple imputation, and then I'm going to mark it and feed the whole thing into the neural network. If you want to do that, take that approach, that might work. Okay, I know this section went a little bit faster than I probably was expecting. So let's just take some time here, maybe a couple minutes, see if you guys have any questions on this, especially the last part. It is somewhat of a survey of techniques. And as far as I know, a lot of this has not been combined with neural networks. So those of you that sort of have some somewhat researchy type of interests, you may want to explore this, see if you can get a paper out of it. And okay, the final one, this final one is actually short and can actually be just described at a high level if you want. Okay, so we talked about imputation, we've talked about missingness, but it turns out if you actually use these clobbering mechanisms, that code that I gave at the beginning where we're just going to construct a artificial set to play with, well, that actually has another useful application. This is just simply anonymizing data. So this technique is actually pretty simple. The thing about anonymizing data is that there is sort of like the legal minimum that you can apply, but sometimes, certainly in my organization, we're a small nonprofit, and we have, in some cases, we end up self-insuring against data breaches. So we're often extra careful about anonymizing things. So if you have someone's vital statistics, but you're moving their name, that might meet the letter of the law, but it still might be possible to infer who the person is. So you want to do something, you may want to do something additionally about scrounging up the data, but still keep it useful. So this is a possible way of doing that. And this is something that we're kind of still exploring, but the technique's actually rather simple. I take my data set, and it might be complete, and I'm going to go through maybe a 5 or 10% pass clobbering the data. Then I'm going to impute it. And then I'm going to do another, I'm just going to repeat this process until there's not that much of the original data left. If the imputation is good, then the data will be still good for my purpose, but it'll be anonymized because the person with the weight of exactly 106.3 pounds doesn't actually exist, but this is the data set. It was close enough to do what I need to do. And the remainder of the example, I just used wine quality for this. I mean, I don't know why you would want to anonymize wine quality, but and they kind of did. They took the manufacturer's name off of it, so they anonymized to the degree they want. But suppose it was healthcare data, somebody who might actually be indicative of a person, especially an outlier. You can still reverse engineer the person if it's more of an outlier. So all this does, I took my original data set that I split apart for training test and I excluded that here with all this. I dropped the type column because for this purpose I didn't want to deal with the categorical. So really all I did here was I took, and since now I'm controlling the way the data is missing, and I know mcar is easier to deal with, I purposely clobber it with mcar. This is one of the luxury, I actually have the luxury of being able to know the type of data, type of missingness mechanism. So I clobber it, here's an iteration. Then I impute it. So I forget what so let's say number 4, acidity 4. I clobber it and impute it. And then, so that's sort of like one pass. And I did, I think, 10%. So I repeat this 10 times, and so most of my data gets clobbered. This is actually something I have not, I know that my organization has been looking at it. I haven't seen anybody else, again, with my poor literature search capabilities, do this. Just something to be mindful of if you actually are, have a need for anonymizing data and yet still preserving a lot of the statistical qualities of that data set. And so that wraps it up. I'm glad you guys stuck with me. In case, any follow-up, and this is actually, it's in slides.pdf is in that GitHub repo. So as long as you keep that GitHub repo, you can get all the resources. I may correct a few of the things I noticed that were wrong here. At some point, I'm going to morph this workshop into the blog we have at West Health. I said that about the last workshop I've conducted, and there's only 2 out of 7 written up for that one. That was a year ago, so bear with me on that. But there are certainly references at the end. They probably go into more statistical detail than definitely more statistical detail than I covered. If you're interested in that stuff, a lot of good deeper articles on this. I'm just trying to cover you at sort of give you the working knowledge rather than the deep statistical knowledge. And if you have anything that's sort of a general question, I'd encourage people to just post issues on GitHub, because then I can address it there, and anyone else with the same question can find it. But my email addresses are here in case you want to contact me directly for some reason or another. And that's pretty, I guess the other thing about GitHub is that actually that kind of guarantees that I get the message around any spam filters I might have. I'm not very diligent about keeping track of those. So that's it. Well, thank you for being a patient group here, and I hope you learned something from us.